So we're on page 23 of your notes, and the things that we're going to be finding limits of are things that look like these three functions right here. So we're going to work these examples. These are called piecewise functions, and they're called piecewise functions because they're broken into different pieces. So the first function has 2 pieces, the second function has 3, and the third function has 2. But we're going to keep the same idea in mind that we covered last lesson. And that lesson is the idea that if the limit from the left and the limit from the right, if they're the same value, then the limit of as x approaches that value does exist. So we need to check the limit from the left. We're going to check the limit from the left. We're going to check the limit from the right to see if they're the same number. If they are, then that is the value of the limit. So let's look at first at this first example. We've got if f of x equals x squared minus 4 if x is less than or equal to 1, or f of x equals negative 3x plus 1 if f of x is greater than 1. I need to erase that stray mark there. Okay, so the way that we're going to do this, we need to check the limit from the left and the limit from the right. So that means I need to split this up into 2 limits. So I'm going to check the limit as x approaches 1, because that's 1 right there, 1 from the left of f of x. And then I'm also going to check the limit as x approaches 1 from the right of f of x. Then I'm trying to figure out, okay, which one's the limit from the left and which one is the limit from the right? So that goes back to the function. So I have this top line. Well, it's not going to let me highlight that part. I have this top line. And it says that the function is x squared minus 4 as long as all the x values that go in for the x are less than 1 or equal to 1. Well, less than 1, those are the values that are on the left of 1. So this is the function I'm going to use for my left-hand limit. I'm going to come over here and circle this part. The second line applies, negative 3x plus 1 applies if the values that you substitute in for x are greater than 1. Well, the numbers that are greater than 1 are on the right side of 1. So this second line is what I'm going to use to find the right hand limit. I'm going to put a blue box around that one. And then to find these limits, we're going to do what you did last lesson. So I'm going to pull up a graph. Now in Delta Math, you don't have that nice option. It doesn't have the table that you put values into, or it doesn't have it already graphed. So you're going to have to do that part on your own. But I'm going to show you how to graph it on Desmos. So you can go to desmos.com. And you can type in a piecewise function. You just have to do it a little bit differently than the way it's written. So I'll show you what it looks like when you type in a piecewise function. So I'm going to type in the first line, y equals x squared minus 4. Nope, that's not it. X squared minus 4, which is a parabola, but I need this to be a piecewise function. And I only want to graph x squared minus 4 as long as the x values that go in for x are less than or equal to 1. So I'm going to use the brace button and say, use that when x, and I need the less than or equal to, so I'm going to use this less than or equal to 1. And then close the brace. And then if you'll notice, that graphs the graph all the way up until I get to less than or equal to 1. Now at this point, I can go ahead and evaluate the left-hand limit because I can approach on this graph. I can look at what happens to the y values as the x values get closer and closer to 1. So as the x values get closer and closer to 1, looks like the y values are getting close to negative 3. And then if I want to double check that, I can click this gear button and pull up a table and type in some x values. So if I want to approach 1 from the left, I'm looking at numbers like 1 or 1.1 from the left. So that would be like 0.9, not 0.0, 0.9, 0.99, 0.999, 0.9999. You see as the x values get closer and closer to 1, the y values are getting closer and closer to -3. So I'm going to come back over here and say that the limit as x approaches 1 from the left of f of x is -3. Okay, so then let me pull Desmos back up so I can do the right-hand limit. Now you can delete this graph if you want, or if you want to keep it up there and see what the whole function looks like together, I can just start a new line. I'll say y equals -3x plus 1, but now I need a brace because I only want to graph that when x is greater than 1. And then I can see that this graph is disjointed, but if I approach it from the right, approach 1 from the right, the y values are getting really close to -2. And then I can double check that if I want by clicking the gear, pull up a table. I need to approach 1 from the right-hand side, so 1.01, 1.001. I'm typing in x values that get really, really close to 1, and they're just barely bigger than 1. And it looks like as the x values get closer and closer to 1 from the right-hand side, the y values get closer and closer to -2. So then the limit as x approaches 1 from the right of f of x looks like that is going to be equal to, I'm waiting on my pen to pop up, -2. Now remember, we said that the left-hand limit and the right-hand limit need to be the same. Well, these are not the same. So since these two are not the same, so since those two are not the same, the limit as x approaches 1 of f of x does not exist. Okay, now let's look at something like the second example. Let me erase all this. Okay, looking at the second example, I am this time trying to find the limit as x approaches 2 of f of x. So again, I'm breaking this up into two limits. The limit as x approaches 2 from the left of f of x. Then I need to find the other side, the limit as x approaches 2 from the right of f of x. Then I have to decide which line approaches 2 from the left and which line approaches 2 from the right. So I go to the function, and I see the first line is x squared plus 3x minus 4 for all the x values that are less than 2. Well, the numbers that are less than 2 are to the left of 2. So I'm going to use that line to evaluate the left-hand function. And then the second line is x cubed minus x for the x values that are greater, the third line, for the x values that are greater than 2. Well, numbers that are greater than 2 are on the right side. So I'll use that there. Now that middle line, f of x equals 4 when x equals 2, we don't need that to find the limit because limits only worry about what happens when the x values approach a specific number. They really don't care what happens when x is a number. So we don't need this for the second part. Okay, so I'm going to pull up the two graphs and we'll evaluate this limit. So now I have my two functions graphed, and I notice that they actually meet up right here, which is really nice. They even though there's a point undefined, it looks like the two graphs, and even if I zoom in really closely, they meet up, which is wonderful. But let's still see what's happening here. Okay, so if I want to approach 2 from the left, that's this red graph. The x values approach 2 from the left. The y values approach this number right here, which happens to be 6. And then as the x values approach 2 from the right, the y values seem to approach the same number. They also approach 6. And then again, if I want to, I can grab the what I want to grab. I want to grab the table for each one. If I want to approach 2 from the left, I can type in like 1.9, 1.99, just to double check to make sure that what I'm seeing on the graph is actually what I'm seeing. So as the x values approach 2, the y values are 5.3, 5.93. These y values get really close to 6, which is what I labeled on my graph. And then let's grab the table for the other one just to double check. As the x values approach 2 from the right, so things like 2.01 is really close to 2, 2.001 is even closer, 2.00001 is even closer. So as the x values get close to 2, the y values get closer and closer to 6. So it looks like when I go back over here, I can grab my pen, as the x values approach 2 from the left, the y values approach 6. As the x values approach 2 from the right, the y values also approach 6. So since these are the same, the limit, the overall limit, like what you would type into Delta Math, as x approaches 2 of f of x, the whole thing equals 6. So this is what you would have for your answer. Okay? Now on our third example, something really interesting happens. Okay, so I've taken this third example, I've split it up into my two limits, one from the left and one from the right. I've graphed it on Desmos. So let's see what happens as the x values approach -3 from the left-hand side of -3. And I'm looking at this blue graph. So as the x values approach -3, the y values are increasing, 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 increasing. That I just hit a bump right there. Increasing. The y values continue to increase. So we're going to say that the y values increase without bound. So that would mean as the x values approach -3 from the left, the y values approach positive infinity. Then, let me pull that graph back up. As the x values approach -3 from the right, the y values are increasing, 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 increasing. The y values also increase without bound. So as x approaches -3 from the right, the y values also approach infinity. And even though these are both infinity, notice they're still the same number. And as long as these are the same number, then the limit as x approaches -3 still does exist. So because I get infinity from the left and infinity from the right, I can say that the overall limit from both sides as x approaches -3 of f of x, that still equals infinity. Okay? Now, when you guys go to do your assignment in Delta Math, you'll see that there is one titled 831, Limits of Piecewise Functions. You'll have 8 in here you have to do, and you have 4 attempts to get each question correct. So you can get as many correct as you want, but your score is going to depend on how many you get correct. Okay, so there's one in here that I want to show you all. So let me find it, and then I'll be back to work it out with you guys. Okay, so there'll be some on Delta Math that aren't like the examples in your notes, but they're still really similar. And it's one like this one, and they only want you to do one side of the limit. So notice right here I have the limit as x approaches 4 from the right of f of x. So you just need to know which line do I use. So I'm going to look at my two lines. The top line is for all the values that are less than 4, which are the ones to the left of 4. The bottom line is for all the x values that are greater than 4. Well, those numbers are on the right of 4, so this is the side that I want to use to come up with my answer. So you can graph this in Desmos, -3 plus x. Pull it over here and get rid of those. Okay, so y equals -3 plus x And I only want that to graph when x is greater than 4. And I'm going to erase this other mess out here. Okay, and I want to approach from the right. So as the x values approach 4 from the right, the y values approach like they approach 1 to get really, really close to 1. So I would just go over here, I would type in 1, submit my answer, and it's correct. So try this assignment. You'll need to get 8 correct to get 100%. If you get 1 correct, you'll see you'll get a 13%. So hopefully you do more than that. If you have any questions about this lesson, please type them into the discussion board. I will review those before our next class meeting. And good luck. If you need any help, you can always schedule a help session. Have a great day, guys.